Okay, so it is a great pleasure to have a special treat today, which is a guest lecture from Dr. Andre Costa, who is the director of the Teletraffic Research Centre here at the University of Adelaide, the TRC. So Andre is a mathematician. He is a PhD graduate from this school. And has been the director of Teletraffic Research Centre for some years now, which is a really interesting centre which takes a lot of the content, the actual optimisation tools that we've been talking about at a theoretical level in this course, and actually applies them in really super real-world industry-focused problems. So it's a really great pleasure to have him to talk about what the pathway is from the stuff that we've been doing in class here into the real world. So he's going to tell us a little bit more about it. So thank you very much.
Thanks, Lewis. So my screen is visible to everyone online, and obviously to you here as well. That's good. And am I on camera? Or is it just the screen? Just the screen. Okay. All right. Thanks everyone online and in person. Thanks for coming today. My name's Andre Costa. I'm director of a centre called the Teletraffic Research Centre that's within the faculty. We're on level 5. Today I want to give you just some very high-level perspectives and things to think about and examples of work that involves the application of the kinds of things you've been learning in your courses, in your mathematics and engineering courses, in their application to industry. As Lewis was saying, I have a background in mathematics. I did honours and PhD here in this department many years ago, and then went and spent some time out in industry, probably about 10 or 12 years, working in various different places, and now have come back to the centre, which does essentially the translation from the academic and theoretical side of things to applied industry projects. So for some of you that might be of interest. It might be something that you will want to hear a little bit more about. Certainly, I remember when I was in third year, I was picking very much applied subjects like Optimisation III, and I was looking for opportunities to see how that could be applied to solve people's real-world problems. So if you're curious about that kind of thing, then that's the kind of information at a very high level that I'm hoping to impart to you today. And you're welcome at the end to come and ask me any questions, or to follow up with Lewis or myself by email about anything we've talked about today. So the centre that I run is called the Teletraffic Research Centre. Teletraffic stands for telecommunications traffic. So what we historically do is work on analysing and optimising telecommunications networks, and we've been going for over 30 years. Initially with some seed funding from what was then Telecom Australia, now known as Telstra after it was privatised. And back then, essentially there were some people in the maths department who specialised in queuing theory and stochastic processes, and that was one of the main ways of analysing telecommunications networks back at that time. Now since then we've had 3G, 4G and now 5G networks, which have completely changed a lot of the technology. And to this day, we're still working with Telstra. They fund a couple of people in our centre essentially to build and run models for them full time. And I'll tell you a little bit more about that. In addition to working for Telstra, over this 30-year time span, we've diversified into a range of different industries. And some of the work we do can be classified as sort of fairly general data science. So people will come to us with a bunch of data, they don't know how to study it, that maybe they sort of have an idea that they could use it for optimization, but they're not quite sure how. So we work with them in order to see whether we can use their data and some of their knowledge about their business processes in order to to help optimise, usually improve some kind of efficiency or reduce their costs. Our centre, there's 12 of us. We're a little bit unusual in the university in that we are fully funded through these industry projects that we do. And by the way, we're always interested to have summer students and that kind of thing. So please do get in touch with Lewis or myself if anything I say today is of interest to you, and we can talk more about opportunities. So this top project here is the one that we're still running for Telstra. As I started saying before, the queuing theory was the dominant way of analysing networks back in the 80s, where basically the optimisation problem was how much copper was required between Melbourne and Sydney, for example, or between pairs of capital cities, in order that people could get their call connected when they picked up the phone. And there was an expectation that 99.9% of the time you'd be able to pick up the phone and call someone in Melbourne without any problems. And that was effectively a queuing problem, which was well understood using queuing theory and stochastic processes. And so hence that was the connection with the maths department. And that particular branch of work. But as I was saying, since then it's become much more data driven. So back then the only data that might have been associated with analysing some of Telstra stuff would have been the rate at which people were trying to place calls, and then typically how long they would be on the phone for. So how long was that, what period of time was that particular bit of copper going to be occupied for, and then when would it be released back into the pool of copper available for connecting calls. Since then it's become much more of a complex system, as you can easily imagine. We've got towers all over the country. They still have to be connected via backbone and possibly fibre beneath, like when your call gets to the cell tower, and then it's got a computer at the bottom of the base station, and it still has to make its way through certain parts of the trunk network and possibly using NBN and so forth. It's a much more heterogeneous system, and there's a lot more data collected at every step of the way, and we focus on the cell tower part. So the work that we currently do for Telstra involves capacity planning for their mobile cell network, and what that means is that every 24 hours our systems pull real-time data from every cell tower in the country, of which there's about 60 to 70,000 cell towers. Every cell tower has heterogeneous equipment on it with different kinds of data. We pull that in, and the model that we run, the model that Telstra employs 2 of our staff to do full-time, is to crunch this data and essentially do forecasting to help them decide where they need to spend capital in order to make sure that people keep getting a good experience in terms of their download and upload data rates. So we use a combination of models and data in order to help inform that kind of decision making. We've done a lot of different projects for all sorts of different industries over that 30-year time frame. So what are some benefits of working with industry? For everyone it's a little bit different. For me, the thing that sparks my interest in it is because I really like to see, to test my knowledge, to see the actual real-world application of the toolkit that I spent years learning, and really understanding the strengths and limitations of that toolkit. So the toolkit you're building up through formal education, like this course, hopefully you're also building that up through some of your own self-directed learning in your own time, just by picking up little bits of programming here and there, or just trying things out. Mucking around with things is really the best way. Anything that grabs your curiosity, just follow it, right? So that self-directed learning will increasingly be the driver of your skill set, and that's something that is worth really cultivating as a skill if you're interested in working with industry, working for industry. And in terms of then applying the work to industry, then there's a range of pathways for you to do that. The obvious one is applying for a job in industry after you graduate, but even if you go on as part of your undergraduate, or if you go on to do a postgraduate degree, the university has industry placement programs that are available, and we can direct you to those. And there's more lightweight type things if you have particular interests. As I said, you can come and talk to Lewis or myself. There's other people in School of Maths or around the faculty who can try and match your interest maybe to something like a shorter term summer type placement or a summer scholarship, that kind of thing. I'll just talk about in a little bit more detail, still at a fairly high level, but a particular application that we worked on in the utilities sector. This is a power utility, an Australian power utility, and we did a piece of work, an ongoing piece of work around analysing job response times. So essentially, when there's some kind of fault or outage with the utility, then we're interested in understanding, modelling the system, and helping to answer some what-if questions about it that revolve around things like what are the optimal resourcing allocations in order to bring the services back online in a timely manner. So I'm purposefully not saying exactly which utilities this is for, but actually the idea and this kind of model is something that we see replicated across different kinds of utilities and systems. So in this scenario, we have over on the left-hand side a series of job streams, right? So they could be faults of different kinds, right? Like fault of a domestic power outage, for example, would be one type. Domestic power outage in a particular regional area. And then the job stream 2 could be, for example, that same kind of power outage but coming in a different regional area. So we have these different kinds of things occurring that raise work that needs to be taken care of by some crew resourcing, so people who go and restore the power, or who reconnect to the water or fix the mains water leakage, whatever it may be, and these arrows here between the jobs and the crews are the first step in our typical modelling work in understanding, engaging with the subject matter experts, engaging with the industry to understand the connections in their system. And so those arrows will represent us building up a picture of when certain jobs are coming in. So people are calling up and saying, I don't have power, or there's a water leak. Then that gets logged in the system, and then there are certain business rules around which resources can go and address that problem. So a very simple kind of business logic is going to be geographically based. So some jobs in a certain area can only be allocated to crews that are nearby. So that's an example of where the arrows are quite specific, right? The arrows are just a general representation here of the idea that an important part of modelling the system is to spend time with, possibly even out actually in the field, and talking to the people who run these systems to understand and build a conceptual and then later a mathematical model of what's going on. And the outcome that we're interested in might be something like the job response times, right? So this could even be a call centre, it could be any kind of system that is like this, and some of those outcomes are what we might want to optimise. So on the bottom left here, on this diagram here, this is showing some real-world data about the arrival rates of a particular kind of job stream, right? So this could be, to reiterate, an example of that could be someone's power goes out, they pick up the phone and they call their service provider. That service provider sees that as a new job arriving in their system. And there's a rate of this, certain number of jobs per hour, right? And as you can imagine, that depends on time of day. So that's what, even though it's, the axes are sort of not really very clearly shown here, that's what this represents. It's showing by hour of day, so in the middle of the night it's quiet, and then 8, 9 a.m. it ramps up because people are waking up and discovering that they don't have service, and then it tapers off towards the end of the day. We can use this real-world data in order to build an hour-by-hour of the day model in a simulation context. So we can build a simulation model of the system that uses this real-world data to then drive the simulation. And so we can then simulate something that approximates reality, and one of the ways we can do that is by breaking things down into hour of day. On the other side here, in analysing then how these jobs are then allocated and worked off, so problems resolved, then we can also look at some real-world data, which usually the industry you're working with will have this data and they can share it with you after you've signed some kind of non-disclosure agreement. And so we might do something like what I've done here, which is to fit a statistical model to the data. And in this case, this is like the labour hours required for a particular type of job. So the blue is the empirical real-world data. This is how it actually looks when you plot it as a histogram. And we can then pick an appropriate model. We can use our knowledge of statistics to decide on which type of model and to generate a model that best fit to that data. And in this case, this happens to be a log normal, and like a lot of real-world data, it has what are sometimes referred to as heavy tails. So a log normal distribution is one that covers small, relatively rare but impactful events out on that right-hand tail, as opposed to, for those of you who have done some statistics, like a nice well-behaved Gaussian or normal distribution, which is often referred to as having thin tails. So the point being here that a lot of real-world problems are characterised by heavy tail distributions and not always nicely behaved distributions like a normal distribution. So that's something you encounter quite a lot. So one way to solve this kind of problem, and for example, you might be asked to optimize the job response time subject to some constraints. So the idea here is that you want to apply some of the optimization algorithms that you've been learning. They could be some kind of line search type method, so who can name some methods you've covered already in the course around optimizing a function f of x? Well, this is typically in multi-dimensions, but there's nothing stopping you reducing it to one dimension if you can parameterize it down to one dimension. So you would have done like the Fibonacci search, maybe, things like that, right? So this is the kind of thing I'm talking about, your bisection search, your golden section search, whatever it may be. This is the realm where you can start to apply that if you have a function f that describes your system. And in the old, going back to that example in telecommunications, it used to be that certain fairly simple queuing models that would describe Telstra's network, they could be written down in a closed form, and so it would look like the kind of, maybe a slightly more complex version of a function that you might get in an assignment. But in any case, you can write it down algebraically and you can probably differentiate it. What we typically work with is a situation where RF is a simulation model that we've built. But that's still valid. You can give it an input, multi-dimensional input X, and you get something out of it. And usually it's a performance metric. It might be cost or some statistic of your job response time. Maybe you're interested in optimizing the average response, or maybe you're interested in optimizing the 90th percentile so that you can then say 90% of our customers won't have to wait more than X number of hours to have their service restored. Right? These are all things that you can get with a simulation model. You might hear the word digital twin thrown around. And really, this could be a function where it's a black box. I've drawn it here as a grey box because we write the code, so we know what goes in there. But there's so much happening. It's just a bunch of code that's not differentiable. We don't really know what's going to come out until we try, right? And so this is where the number of calls to your black box, you want to minimise it, right? Because running this simulation might take a few days. So that's where your efficiency of a search algorithm becomes important. So that's part of the rationale behind like your golden section and so forth. They're strategies for minimising the number of calls to your f of x. And if your f of x is cheap, you don't really care. You could just do a really, really dumb search. Right? If it's really cheap, you could even just kind of go along in increments. But the whole rationale for trying to do clever line search methods is around the idea that your calculation of f of x might take you a long time. So you want to be parsimonious with calling it. So because we are fairly product focused, we try and build these sorts of things for our clients in a way that is then usable to them, rather than us just telling them the right answer. We usually try and build some kind of application that they can interact with to help them answer the questions. And so what's on this page, these are some examples of providing graphical input to that X, right? So the input are a collection of parameters and decision variables. The parameters are just attributes of the system, like the job arrival rates. You can't do anything about those. But your decision variables that are the part of the input, as you'll know from the subject you're studying, they're the things that you have control over that you can optimize. In this example, it's the crew resourcing. How many people you put to work in different parts of the system and for how long. Right? How long do they need to be on call? Right? Those kinds of things. And this is just showing an example of the graphical input that we provide to specify those inputs. And then what we get out the other end is some performance metric. And so here we're doing a series of experiments that you can think of kind of like a line search, where we're trying to find the zero of a function. On this slide it's showing an example where we're looking to find a zero, where our KPI of the performance metric, which is, let's say, the black line, let's say we pick the average of our job closing time. Let's say we want that to be below some target KPI. But we don't want to throw more resources at the problem than we need to. Like, obviously, if you throw more and more crew, it's going to be more expensive and we can overshoot. Hence, we can cast this as looking to find the zero of the KPI hitting the target. We don't want to do better than what we're needing to, because that'll just cost more money. At some point you have to trade off, right? So this is an example of where you can use your simulation model, f of x that you've built, but you treat it then, after you've done that and you've validated, you treat it as a black box, and you can call it with the sorts of search algorithms that you've been exposed to in this course. Even if the model is really complex and you can't differentiate it and so forth. So just to wrap up, here's my personal reflections, my rough guide to working on industry projects. First step is really spending the time to understand the business problem, the key drivers, spend time with the end users of the thing that you will be building or solving. And this is often the hardest part, and people will say they think they need X, but after further discussions and iterations, it turns out they actually need X dash. And that is often one of the most interesting and challenging parts of the project, really sort of getting a common language. And that's where having, let's call them soft skills, of being able to engage with people who might not be mathematical specialists at all, to engage with them, to understand, to sort of meet them on their language, but then translate that back to the language and toolkit that you know. Almost certainly you'll have to use some historical data to calibrate, validate or parameterize your model. and you'll probably need to spend some time pre-processing or cleaning the data. And so anything that you can do to develop your skills in this is going to be time very well spent. And it's not always the sexiest thing. Data cleaning is an important skill in itself, and hence why data science, everyone goes on about data science. Well, a part of that is actually learning some more systematic techniques for pre-processing and handling large volumes of data that might go into a really nice, well-behaved model. Before you can even do that, you need to be sort of interfacing with that real-world data, and that's a very important skill. Anytime you spend investing in your own skills to handle that is time very well spent. Also, part of cleaning doesn't mean just getting rid of stuff that is inconvenient. So you might be familiar with Marie Kondo's decluttering. You sort of want to declutter your data, you want to declutter your house, and you pick something up and ask, does it spark joy? And I found this Twitter post which I thought was very amusing. Throw away whichever data points don't spark joy. And so don't do this. Do not do this. That's all I'll say on it. There's a lot to be said about data cleaning, and people will say, outliers, I got rid of it because it was an outlier. Well, was it really? That's actually a hard question. So just be prepared for some interesting depth and complexity around these sorts of things as you move forward into a problem. Then you can prototype a model and a solution. So this might be actually writing down some equations on paper that you think capture what you've heard, your understanding of the system. It might mean going away and writing some code that represents a model of the system. Whichever it may be, it's always valuable to have a tight feedback. So you will have heard agile methods, agile development methods, agile project management. This is all very real when it comes to then feeding back what you're coming up with as you're doing it, and early prototypes with the end users, with the clients, if they're industry clients, and you iterate. So the iteration is a very important part. It's not the case that you go away for 3 months and build something and then come back and say, here it is finished. The best way to work is really by having a lot of fairly tight feedback cycles and validation, and then constantly checking what you're doing back against real world data, back against subject matter experts who can say, oh no, that's definitely wrong. And then that can save you like a month of work with you thinking that you're on the right track, working alone in your office. So where possible, structure it so that you can have those feedback cycles. Where possible, minimize the gap between prototyping and production. And this all comes down to a good choice of your toolkit. What I mean by that is, let's say you're building a system that generates a report for a particular efficiency over the past week, and you sort of build that up into a dashboard. Then let's say you're asked, oh, that's good, but actually can you display this other metric for us as well? Then a good measure of whether you've built this kind of minimized gap between prototyping and production is how long does it take you for you to code up and drop in this new metric into your system. If it's you're looking to build something whereby it's really easy for you to drop in a new one of these. If you've achieved this kind of agile approach, I think one measure of it is if you get asked to drop in a new metric, it's not like, oh, I'm going to have to go away and rewrite the whole code. Right? I can just drop in another thing and it'll just come to life. And that's important to be able to be responsive, because one thing that you can expect is that there will be constant change. So if all goes well and the client is happy with what you've done, then they're going to want you to keep improving things. So it's you want to engineer for change. And then finally, don't reinvent the wheel. Use existing industry standard open source libraries. Now is the better time than ever in terms of access to open source libraries and options for you to implement these algorithms. As a general rule, you don't need to be reinventing the wheel. You don't need to be writing all of your own algorithms from scratch, even though that's the best way to learn about them. But then you've spent the time learning, you understand what's going on conceptually, then you can, when it comes to delivering things, lean as much as possible on existing infrastructure. And so for those of you who aren't familiar with things like this, we use Python a lot, and Python is good because it has a very deep library of existing implementations of common statistics and optimization methods that we need to use. So, you make use of those, don't reinvent the wheel. For those of you, I imagine most of you have had some exposure to programming, but again, like spend some time looking around at the options. So you have Python, you have R, you have other languages. Really spend some time mucking around with things, and that's easier than it has ever been at any time in the past. Just an anecdote towards that, and then I'll finish up. That's really everything I wanted to say. But in terms of it really being a golden age for you as a cohort to be doing this stuff, some of you are familiar with Google's TensorFlow library. TensorFlow is a machine learning neural network library that was open sourced a few years ago by Google, and Google used it in-house for many years to do all of the kinds of optimizations they do for us, for users, and obviously they've used it to monetize, and their model has been monetizing people's data, and they open sourced the tools that they were using to do this. And someone asked them, well, aren't you giving away the crown jewels? Why are you just making all of this proprietary code that you've spent years building in-house? Why have you just open sourced that? And they said, well, because the real value is in the data. The algorithms, we're happy to share them. So that's good in a sense that you can go and use them for whatever project that you're working on, and so you're getting the benefits of all of that work that has been done. And that's a good example of it really being a golden era for you as a cohort to make use of all of these tools that are available to you, and then you can apply it for whatever project you're working on. So that's the end of my presentation.
Thank you. Questions for Andre? And I should say I'll go to the front of the room so that the microphone picks me up. There are people online who want to ask questions as well that I'm monitoring the chat window on Eco 360. But please ask away.
Have you ever used deep learning for your work? Does that pop up much?
Yeah, so we've used some machine learning for predicting upcoming workload in example. That's looking at previous history, like recent history, taking into account things like weather and stress, lead up stress in the system to predicting what's going to happen next. So yes, we have done that. Yeah. And we've applied not just deep learning. So deep learning would be like neural network type model, but that's not the only class of machine learning model. In that particular project, so we tried some neural networks, but actually the ones that seemed to work just as well, if not better, and certainly simpler to manage in that case, was some random forest algorithms, which you've probably also heard of. And again, that's all available as open source libraries for you to just plug and play and try different things quickly, see what works best.
Is deep learning going to put you out of a job, like in your example that you gave? Could I just chuck that data into data that the customer gives you into a neural network, into some coming advanced AI, and replace consulting?
It's possible. Yeah, we all have to.
I didn't think that was going to be the end of it. To explain why that's not the case.
Well, like anything that can be automated, and more stuff is being automated. I suppose the crux of your question is, could the building of the digital twin type model be automated just from looking at data? And I think we're quite a way off that. We're quite a way off that because there's still making sense of the semantics of the problem, understanding, being able to differentiate, understanding what unstructured data actually is. When someone tells you, a human can easily say, right, that's that. I think the amount of AI overhead that it would take for someone to be able to just throw completely unstructured data with very little guidance, and for an AI to build a simulation model of the system from it is probably still a way off, but who knows?
I think that's the right answer.
Yeah.
If that future is coming, it's a long way off, and there's the modelling skills that you talk about remain important. Other questions? So I have another sort of leading questions.
I didn't realise that was a leading question.
You've done the course that these students are doing, and have done the degree that they're all engaged in, and you work in something. You do stuff now that, to me, as an applied mathematician, a lot of these 6 points seem pretty different to the stuff that I wrote about learning. It's there's a lot of software development and coding and statistics, and stuff in here. What is it from your background as an applied mathematician, and somebody who has a very similar background to the maths degrees that these guys are going through, what are the skills that you got from that you feel like you most use right now?
Well, I think knowing the more inner workings of the algorithms you're working with, I think, like you mentioned, deep learning, I think more and more there's going to be packages, even soon in Excel, where you can right-click machine learning. And that will work for nice well-behaved cases, maybe 50, 60, 70% of problems if people are trying to do simple things. But when things go wrong, which is in any kind of complex real-world situation, when I say when things go wrong, is like when the results, your initial results, are probably not right and need some rethinking and some deep thinking about what's going on. Part of that is going to relate to your understanding of the real world and mapping it to your problem. But another part of that, it can actually be just understanding that your algorithm hasn't converged properly, and knowing what convergence means, and having some good intuition for what the minimizing the sum of squares search gradient descent in the neural network is actually trying to do under the hood, just gives you that edge in terms of having a holistic problem-solving view. And you will need to, you will need to do problem-solving and debugging of your modelling and your code and your interpretation of the real world and its interface to your model. And so you're at a big advantage if you know what the inner workings of the things that you're asking the algorithm to do, compared with someone who will just right-click, do machine learning. Here's an answer. It doesn't really make sense, but I've got no idea where to even begin to analyze a diagnostic. Whereas if you know your convergence, if you know how to interpret convergence diagnostics for a search algorithm, because you've studied it and you understand intuitively what that means, then that's the value, I think, of that's the value add you bring as someone who's trained in this, rather than someone who is just an Excel user.
Anything else? So yeah, so I'm thrilled that you brought up the examples that you had. Your example with the expensive black box effects that can't be differentiated to run, because that's exactly why we talk in the course about the efficiency of these algorithms, and spend a lot of time talking about the counting, figuring out the number of function evaluations and things like this. It's a concrete case where it's really important. I'm also thrilled that you showed SciPy docs for SciPy.optimize, and an anaconda there at the end, because I can show you what my backup teaching material was for today.
Yeah, good.
If you had time, one of the things that we do in this slide
Excellent.
has been introducing optimization in Python.
Oh, that's fantastic.
If you hadn't been here, we'd be just up to the stage today of playing with exactly sci-fi.demise.
Oh, all right. Well, that's good. And I didn't know that. We didn't talk really about what was going to be there.
So, it was the perfect.
Yeah, so I didn't throw that in at Lewis's request at all. I didn't even know that you were doing that kind of stuff in this course, although I imagine you probably would be, and I'm glad to hear you are. I've used Python almost every day for the past 12 years in actual applications. So you can do real world stuff with it, and the limit is really just your skill and imagination. So anytime you invest in doing that, it doesn't have to be Python, but Python is kind of currently, you're going to be able to get hired on the basis of having good Python skills, because if you look around, as I'm sure you have job ads, there's demand specifically for, you must be able to code with Python.
But I think your point as well about understanding how these things work under the hood.
Yeah.
The classes spend a lot of time coding these things up, getting these algorithms up in MATLAB or running them through by hand. A lot about really understanding deeply how they work. And I think that's once you have that understanding, the great time is going to start playing with these algorithms. Python doing that work too. Thank you. The kiddos, sorry, I call you kids. Like my children. If people want to get involved and find out more, how do they contact you?
So there's my email on the first slide. Feel free to contact myself or Lewis. There are plenty of people also in the School of Maths who can connect you to industry projects as well, and indeed across the faculty if you're doing other subjects. If it's something you're interested in, ask around.
And you mentioned summer projects, projects, things like this. You have opportunities there and supervise students and things like that. If people are interested, then come and talk to them. Andre or I.
All right, thanks everyone, and good luck.
If you'd been a few weeks earlier, I would have built one of your examples into the final exam.
Oh yeah,
It's written now. So.
You're off the hook. So I'll just unplug this and
Yes.
shut it down.